The next problem we are going to prove hardness of is graph coloring. So we are given a graph and we'd like to color it. So a quick reminder what the problem is. I give you a graph and an integer k, and I ask, can you color the vertices using k colors, right? A coloring, to remind you, is you're assigning every vertex a color, which is, you can think about it just a number between 1 and k, an integer number, and not two vertices connected by an edge can have the same number, the same color, right? So this is, for example, a valid coloring, right? Red, no two colors are the same. Notice that if you look on all the red vertices or all the blue vertices, they are forming an independent set. So really, when I ask you whether the graph can be colored by k colors, the real question is, can you break the graph into k independent sets? So intuitively, it's this problem is harder than independent set, right? And in fact, coloring is one of the hardest problems in NP at some level because it cannot really be approximated well. Let's not go into these details, but just as a side comment. Okay, coloring a graph with two colors is easy, right? You just have to decide if a graph is bipartite. How do you do it? Well, just do BFS on the graph, right? You know, if you do a BFS on the graph, to remind you, you get layers, right? You get layers of the graph. The important thing is that now you have layers L1, L2, and so on. And the idea is that all the even layers have to be the same color if you're coloring with two colors, because all the even and odd layers that are consecutive have to be of different colors, right? If you're using two colors, it must be that the even layers must be 0, let's try again. All the even layers must be one color, all the odd layers must be another color. And a graph, of course, is not too colorable if there is an edge, a cross edge in the same level, right? An edge with between two vertices in the same layer, then you essentially are going to not be able to color it by two graphs. One can show that the graph is bipartite if and only if there is no odd cycle. But in any case, you just do BFS, and if there are no cross edges, then you know the graph is bipartite, namely it's two colorable, right? Even odd colors, and you know the coloring. So two coloring is really easy, and the surprising thing is that three coloring is already NP complete. By the way, this is a phenomenon that is quite common to NP complete problems. You have some parameters. If the parameter is below a certain value, the problem is tractable. We know how to solve it efficiently. You increase the value across some value, and suddenly it becomes hard. We saw the same thing with SAT, right? 2SAT is easy. It can be solved in linear time. We didn't show how, but it is. But on the other hand, if you increase the number of variables from in a closed SAT formula from 2 to 3, suddenly the problem is much harder, right? So part of the fun of this wool stuff is to figure out where is this transitioning happening, right? And whether a parameter really matters or doesn't matter about the hardness of the problem. Okay, so this is the problem. Next, we will start dealing with the reduction.